Welcome back to the Deep Dive, where we tear open the sources you've shared with us and explore the most critical, game-changing moments in technology. Today, we're diving into something that really should have been impossible. We're talking about the secret history of Moore's Law.
It's a fantastic story. It's really all about how the microchip industry just refused to obey the laws of physics.
Exactly. And the core problem was light. I mean, you're using 193 nanometer immersion light, but you need to draw features way, way smaller than that.
Right. Traditional lithography just hit a hard wall. The industry needed to get below an 80 nanometer minimum pitch, and the light source just couldn't do it.
So that's the puzzle for you, the listener. How do you draw a line that's, say, 20 nanometers wide using a crayon that's 193 nanometers wide? It feels like black magic.
Well, the answer turned out to be multi-patterning lithography, or MPL, and it boils down to something really simple.
The kiss.
Be incredibly inefficient. I mean, instead of doing it all in one perfect single shot, you split the pattern up and print it in 2, 3, or even 4 painstaking steps.
And it's important to stress, this wasn't just some clever lab trick. The sources make it clear MPL was absolutely essential for survival.
Oh, completely. It was the bridge technology. Everyone was waiting for the next big thing. Extreme ultraviolet lithography, EUV.
Which was famously delayed.
Massively delayed. It was promised for, what, the 10 nanometer and 7 nanometer nodes around 2015, 2017. It just wasn't ready. MPL kept the whole industry on schedule.
So its mission was basically to multiply the number of features you could get from a single light source. If you were to break down that basic workflow, what does it look like?
It's a few key stages. First is pattern division, where you take the final design and algorithmically split it into simpler pieces.
Okay.
Then you do sequential exposure and development for each of those pieces. After that comes pattern transfer, that's the etching. And when you combine all of those steps, you get your final super dense pattern.
And our sources point to two really different ways of doing that first step, the pattern division part.
That's right. You've got pitch splitting on one hand, which is things like LELE, and then you have a more elegant solution called sidewall image transfer, or SIT. That's where SADP comes in.
Okay, let's start with the simplest one then. Litho-etch. Litho-etch. LELE. It sounds like exactly what it is.
It is. It's the most straightforward approach. You print and etch half your lines with one mask, mask A.
Right.
Then you come back, put down a new layer of photoresist, and you print and etch the other half of the lines with mask B, right in between the first set. Boom, double the density.
And if you need even more density, you just keep going. LLEA for triple patterning.
Yep. They use triple patterning for some really critical layers at the 14 nanometer node, and it even went up to quadruple patterning, LELE.
But that sounds risky. What's the biggest danger when you're trying to print one pattern perfectly on top of another one?
You've hit on its fatal flaw.
It has to be alignment, overlay.
Overlay. It's the Achilles heel of the whole process. If mask A and mask B are misaligned by even a few nanometers, your yield just collapses.
And every extra step, LELE, just compounds that risk.
Exactly. It's a nightmare for process control.
So that risk leads us directly to the smarter solution, right?
Yeah.
Self-aligned double patterning, or SADP.
This is where the engineering gets really clever. SADP is designed to completely eliminate that mask-to-mask overlay error.
How does it manage that self-alignment?
Okay, so you start by printing a core pattern. We call it a mandrel. Think of it like a temporary placeholder.
Got it, a mold.
Exactly. Then you deposit a thin film, a spacer material, over the entire surface, blanketing the mandrel.
Okay.
The magic step is the etch back. You etch away that spacer material from all the flat surfaces, leaving it behind only on the vertical side walls of the mandrel.
Ah, so you're left with these two little walls on either side of your original line.
Precisely. Then you just remove the original mandrel, and you're left with 2 spacers for every one line you printed. You've doubled your density, but their position relative to each other is perfect. It's defined by physics, not by a second alignment.
That is genuinely elegant.
Yeah.
And that self-alignment is what lets you take the next leap, right? To the density champion, self-aligned quadruple patterning, SAQP.
Yes. SAQP is just applying the SADP process twice. It's almost that simple.
You just run it again.
You run it again. The spacers you created in the first SADP step, they become the mandrels for a second SADP step.
Yep.
It effectively quarters your original pitch.
And the numbers on that are just staggering. The sources say you can take a 76 nanometer pitch from your immersion tool and with SAQP, shrink it all the way down to a 19 nanometer final pitch.
It's how we got the fins for FinFETs at 7 nanometer and 5 nanometer. It's also how Intel hit their very aggressive 36 nanometer metal pitch on their 10 nanometer node. It was the only way.
Okay, but this level of complexity has to come with a truly shocking price tag.
Yeah.
All these extra steps. What did that do to the cost of manufacturing a wafer?
It's a huge jump. The complexity and the cost are directly linked. The data we have shows that if you set a normal single exposure process at a baseline cost of 1, then SADP is already double that, 2x the cost, and SAQP is 3x. It's a massive financial barrier, and it's one of the big reasons why fewer and fewer companies can afford to play at these advanced nodes.
But here's the part I found fascinating and a little counterintuitive. Your source data put EUV single exposure at a normalized cost of 4x.
That's right.
So it could actually be cheaper to do a 4-step DUV process like SAQP than it is to do a 1-step EUV process.
It's a really key trade-off. Even with 4 separate passes, the old immersion scanners are mature, very fast machines. They have a higher wafer per hour throughput than a lot of the early EUV tools. So the overall cost isn't just about the number of steps. It's also about tool uptime and speed.
Whether it's 3x or 4x, though, the manufacturing challenge is just extreme precision. We talked about overlay for LELE, but for all of them, you need insane control over feature size, what you call CD, and focus.
Absolutely. CD is critical dimension, width of your lines. And keeping that, plus focus and overlay within tolerance, is just a monumental challenge. I mean, ASML's latest immersion scanners have achieved sub 3 nanometer matched machine overlay.
Sub 3 nanometers on a machine the size of a city bus. That's incredible.
And you can't do that without incredibly sophisticated software. You have things like process window enhancement, PWE, which is all about finding the safest combination of focus and energy dose to print a pattern reliably.
And the ultimate version of that seems to be source mask optimization, or SMO.
SMO is a game changer. It co-optimizes the light source itself inside the scanner and the pattern on the mask simultaneously to get the best possible result. One paper showed SMO created a 23% larger process window for a 10 nanometer layer. It makes unmanufacturable designs manufacturable.
Okay, that's the manufacturing side. Let's pivot to the design side, which honestly sounds like a complete logistical nightmare. It starts with this problem called layout decomposition, or coloring.
Right. Coloring is the EDA challenge. How do you take the final design that the chip architect wants and mathematically split it into 2, 3, or 4 different colored masks without breaking any rules?
And what are the goals there? Just make it fit.
It's more than that. First, obviously no conflicts. Second, you have to minimize stitches. That's where one line gets split between 2 colors, a huge overlay risk for LELE.
Okay.
And third, you need color balancing. You want each mask to have a similar amount of stuff on it, a similar density, so that the etch process behaves predictably.
And this is where the math gets, frankly, terrifying. For double patterning, it's hard enough.
Yeah.
But the sources say that for triple or quadruple patterning, the problem is NP complete.
Yeah, and that phrase should send a shiver down any computer scientist's spine. It basically means the problem is so complex that finding a perfect optimal solution could take, the lifetime of the universe for a full chip.
So, how'd they solve it?
They cheat. Well, they use approximations. They use these complex constraint models, like semi-definite programming relaxations, to just force the problem into a state that's solvable in a reasonable amount of time. It's not perfect, but it's good enough.
And this complexity completely changes the rulebook for designers. You can't just have one spacing rule anymore.
Exactly. Now you need 2. You have one tighter spacing rule for shapes on different colored masks and a much wider spacing rule for shapes on the same colored mask.
And that leads to these really weird new design checks, like the odd cycle check for double patterning.
An odd cycle, right. If you have, say, 3 features that are all too close to each other, you can't color them with just 2 colors. One will always conflict. It's mathematically impossible.
Which is why this all has to be considered way earlier in the design flow. It's not an afterthought.
No, you can't wait. That's what design technology co-optimization, or DTCO, is all about. You find these coloring conflicts between standard cells during placement, and you fix them then and there by flipping a cell, shifting it, recoloring it. If you wait, it's too late.
Okay, let's talk about a necessary evil that comes up in almost all of these flows. The cut mask.
Ah, the cut mask. Yeah. So MPL is fantastic at making very dense parallel lines. What it's terrible at is creating the ends of those lines.
The tip-to-tip spacing.
The tip-to-tip spacing. Without a separate step, the gap you'd need to leave between the ends of 2 lines would be huge, which wastes a ton of space.
So the cut mask doesn't add density. It just comes in at the end and chops the long lines into the smaller functional segments you actually need.
That's it exactly. And here's the kicker. Even EUV, the technology that was supposed to fix all of this, still needs cut masks or similar cutting approach. Its single exposure also struggles with that tip to tip control at the bleeding edge.
That feels like a really important point. EUV is not the silver bullet everyone thought it was.
It's incredibly powerful, but it's not perfect. It has its own unique problem, mainly stochastic defects.
Random errors.
Yeah, random errors where at these tiny dimensions, a feature might just not form correctly, or two lines might randomly bridge together. It's a fundamental challenge with the physics of EUV, and it's possible multi-patterning might be needed again someday to help solve it.
Speaking of other solutions, the sources briefly mentioned directed self-assembly, DSA.
DSA is really cool. It uses block copolymers, basically special plastics that assemble themselves into tiny patterns under 20 nanometers. The promise is huge. Simpler processing, fewer masks.
Yeah.
But the defect rates are still way too high for high volume manufacturing. It's been a promising research topic for a decade, but it's not quite ready for prime time.
So if you put it all together, it sounds like the future for now is hybrid.
Absolutely. The leading edge is all about hybrid flows. Things like SALI, which combines the self-aligned process for your dense lines and then uses the more flexible LELE approach for the cuts. At the end of the day, it all comes back to that DTCO principle. You cannot design a modern chip without building these incredibly complex manufacturing constraints in from the very beginning.
So we started this deep dive with Moore's law hitting a brick wall at 80 nanometers. And through sheer brute force and mathematical genius, MPL dragged it, kicking and screaming, all the way down into the sub 20 nanometer world.
We went from a simple but risky two-step dance to these incredibly convoluted, self-aligned four-step processes, all just to pattern a single layer of a chip.
Right.
And that brings me to a final provocative thought for you to chew on. We established that DUV quadruple patterning is about 3x the cost of a single exposure, while EUV is 4x.
Okay.
If EUV keeps struggling with stochastics and tip-to-tip issues, maybe forcing the industry to push DUV even further to 5, maybe 6 patterning steps for a critical layer,
Yeah.
you have to wonder, are we even fighting a battle against optics anymore? Or are we fighting a battle against probability where the sheer staggering number of process steps required makes a catastrophic failure on any given wafer almost inevitable?
A battle against complexity itself. That is a huge question of diminishing returns. Thank you for making this deep dive possible. We'll see you next time.